ready. Yeah, I see him now. Great. So we have a lineup of speakers here, and the intent of this session is really to do a joint working session for the first time between the security team and the OSF team. And we've lined up a series of topics around how security and OSF basically match together. I don't think you see me on the video, right? Just realized I need to turn on the video. Why isn't that happening? I have no idea. Okay, I'll fix it later. Okay, so the intent is to do a joint session between security and OSF. Every topic will be moderated by a different person. I'll run through the slides. And the idea here is to start with a 15-minute kind of like intro about OCP security, specifically focused around secure firmware, which Ben will walk you through, and we'll talk a little bit about the security badge thinking of the security group. Then we have a discussion around the open system firmware ownership, which Ryan will be leading. Then it's a discussion around what type of firmware do we think should be allowed into OSF? And I think, Ron, you're going to take the lead on that, right?
Yeah.
Yeah, no, maybe.
Where is that?
The mean buffer types of firmware to be allowed for
in the
OSF
ownership section? Or?
Yeah. Okay, and
okay.
then
Sure.
Excellent. And then we have a discussion around the SMI handlers.
Yeah.
And last, we'll talk about how to get more vendors to comply with OSF and security requirements. So without further ado, let's get started with the secure firmware development. Ben, your stage. Ben? By the way, Katie tells me I can't start the video because the host stopped it. So I don't know if you want to fix it.
Are you trying to play a video?
No, I was trying to start my camera and it tells me I can't. Maybe it's not a Zoom thing. Maybe it's something on my PC. So I'll just go ahead without video.
Okay.
We can't hear Ben.
Ben, if you're speaking, we can't hear you. It doesn't look like you're on mute, but we can't hear you. He said he's having a mic issue.
Maybe while we wait for Ben to fix the mic issue, I'll skip to the next slide and talk a little bit about the security badge requirements, and then we'll go back to Ben. Hopefully, you'll fix the audio issues. So Ben is going to talk about a document that the CSIS and OCP security basically prepared together that talks deeply around how to write secure firmware, how to develop firmware to be secure. I want to give the OCP security perspective on how this fits into the set of requirements that we're working on for defining security badges for 2021, mainly meaning what would a vendor need to do in order to say I am compliant with the security requirements. So this is still work in progress. We have some thoughts about how this will end up looking like. We still need to socialize it and get it approved by the OCP IC committee, but we would like to share like the current thinking. So first of all, at the OCP security, there are a set of specs, feature requirements, which we've been discussing in previous session for secure boot, attestation, recovery will be coming up, etc. There is also a threat model, which is covered by the security threat scope document that covers different basically threat vectors and how they map to what vendors need to implement or do in order to be mitigating this threat. And from this threat model, we will expect vendors to provide some kind of a document or collateral or conformance statement that explains how they deal with the security requirements. And it's built as a threat, as a series of questions around how do you deal with threat X? And there is an enumeration of threats based on the threat model. The secure firmware development requirement, which Ben is hopefully going to talk about in a few minutes, is baked into the conformance statement. So some of the threats are addressed by feature. So like how do you ensure that only correct firmware loads is basically what secure boot and attestation does. But there are also threats that talks about how do you ensure that you minimize the number of vulnerabilities in the code. How do you ensure you basically followed good development practices, and the secure firmware development is the checklist from the security perspective of things to comply. The way we are thinking about it in the OCP security group is that we want to land on 3 levels of compliance for 2021, bronze, silver, and gold, where bronze represents the thing that really should be achievable by all vendors pretty quickly. And it encompasses supporting all of the hard requirements of secure boot and attestation and providing a conformance statement. So basically, we want visibility from vendors. We want the right minimum features, and we want visibility from them. We want to encourage vendors to think about the threat model and actually document, hey, here is what we're doing to address different threats. And that by itself, we believe is a great start to get bronze level. Yes, Ben. Now we can hear you. Good. So let me finish this slide and then go back to yours. Silver is the next level. So everything around bronze plus recovery, which is still a spec in progress, but we hope to finalize it in the coming month. And some requirements around opening up some of the codes or doing some certifications. We are still discussing those specifics. And gold is where you really shine and you do everything around silver, and you also should support the shoulds, the optional requirements that are not must, but really important, good to have, and also open source. So if you want to go for gold, you're expected to open source your at least your security pieces of the code. We haven't yet defined exactly which pieces, but the way I think about it is all of the critical security pieces should be open source to be OCP gold badge, right? We're still, as I started, we are still waiting on. We still need to do some work here to clearly define this. We are aiming for completing and approving this in early 2021. So hopefully by the next summit, this will be a requirement from vendors to comply. But we wanted to give you some visibility into what we are thinking of, and also tied back to the secure firmware development. So were there any questions on that while I was speaking? Anything on the chat window? I can't see it. Okay. So I'll hand it over to you, Ben, to talk about the secure firmware development best practices.
Thanks, Gal. So this is meant to be in a previous conference, OCP conference, we went over the secure development best practices document, which is linked below, in detail, but not with respect to any particular project. So we have a short amount of time here, and I wanted to go over the Linux boot project as it lines up with our previous document. And we're not going to be able to cover anything in too great detail, but one of the interesting problems on Linux boot is it's developed in fairly large corporations, primarily Google and Facebook, and it's moved to an open source project. And how are other entities, or how we're going to co-develop Linux boot and uroot or boot in a way that results in a secure product. So Ryan and I had a quick chat to kind of go over this, but certainly Ron or other members of the Linux boot project, if you're on the line, feel free to speak up. I just want to kind of breeze through these things. We'll have time in our open discussion later on to go in greater depth. If we identify areas that are available for people to contribute or areas that need to be improved, please point those out. So Ryan or Ron, are you here?
Yeah, I'm here, Ben.
Great. So let's kind of go through these.
I'm here. My audio is so bad. I'm trying not to talk too much.
Okay. In a large corporation like Google, there's a lot of infrastructure to take care of a bunch of these problems, and a project like Linux boot done in that context doesn't have to worry too much about things like source code control. But as we move out to this collaborative open source project, or it's where Linux boot has always lived. How do we achieve those goals? One thing which has the participants are a long time in this boot firmware, threat models kind of understood implicitly, but it bears looking at as because the threats change over time. What I think this might be an area for contribution, but what can you say about the threat model that you're operating with? Ryan?
I guess generally in terms of Linux boot, it's really up to the implementer. Linux boot itself doesn't have a clear definition of its threat model, but it's really up to who's using it to define their own threat model and do that necessary work. Of course, you're starting with Linux, so you get all the advantages of, like, compared to other firmware, you have the benefit of protections such as user mode or capabilities and things like that, which protect you a lot better than like compared to having all your firmware in ring 0, etc.
Yeah. So for the full system deployed in a data center, we're of course going to be, and it's going to be touched on in some of these other points, but supply chain attacks and maybe malicious contributors, maybe folks who haven't done proper or testing according to the expectations of the developer, and not necessarily what the software is going to be exposed to in the real world or through malicious actions. So security exceptions, compromises. There's a practical reality that product needs to be delivered, and you're holding up other areas of development if you don't give people something they can use. I have to extend my car warranty otherwise, so I'm under threat of attack. I don't know if you can hear that.
I think you're experiencing a DOS attack.
Yeah. So anyway, for instance, if you are there areas that you would like to have addressed better than you have, but have not yet gotten around to? And how do you keep track of those? Your technical debt, for instance.
So in terms of Linux boot, probably I'd say the community, we kind of rely heavily on kind of the Linux kernel. For Linux boot, typically there are very few patches that you would see on top of upstream. It's mostly just an upstream kernel. So for contributors to Linux boot, most of the changes would be in user space, like in a project such as uroot, and things like technical debt or possible improvements would mostly be related to user space applications such as uroot. And there are definitely areas of improvement that we would like to see there. For example, one that isn't so related to security, but improvement in possible boot targets, such as being able to boot things like Windows or other operating systems.
So that leads to indirectly the ability for this to be ubiquitous system firmware, therefore having more contributors, therefore more attention, higher quality. So kind of indirect as far as security goes. Signing, I think, was covered pretty well in the 2 morning sessions. And it's something that certainly your team within Google, you are certainly aware of it, but it's not something that, it's not a part that your team, your development team adds. I think we can leave it to the previous 2 sessions this morning for now. And so best practices, principle least privilege. When we compare this to the industry de facto standard of UEFI, where it's all one address space, all one set of permissions, any line of code can do most anything it wants, with possible exception of SMI or other special contexts. Certainly you get we discussed this before, you get the advantage of Linux. But one of the interesting things in Linux boot is the removal of, you mentioned in our previous discussion, removal of the concept of a user. So one would typically, in a Linux implementation, try to run things as different users and not have processes run as root. What's the answer to that in Linux boot?
Yeah, so currently in Linux boot, at least for the implementation you would find in uroot, in the config, we've disabled multiple users. I think I see Ron is back on. He might be able to speak more about that. But currently we've disabled a lot of options in order to save for a flash size. But if it was deemed necessary, I suppose you could re-enable things like multiple users so that certain applications can run as a sub-process in a more restricted capability set, or in a true root, or something similar to AppArmor.
Has the capability system also been removed, or does that remain intact?
The capability system, I believe, is also removed. But this is just based off of the config set we have inside of uroot.
Mm-hmm.
Yeah, the model of Linux boot was generally that it was intended to be there, run basically maybe 1 or 2 programs and be gone. So we've been doing Linux. I've been doing Linux boot or its predecessors for a pretty long time, and when we ran it in the HPC world, we never really hit a need for the multiple user thing, but certainly if such a need arose, it's not a big deal to turn it on. But I have to wonder though, the multiple user thing to me almost comes with an attendant thought around persistence of the things that are running as different users. So I've never really been sure that we really needed anything else, given how short a time Linux boot is supposed to be around. But if it was felt to be needed, it's certainly no problem to put it back.
Yeah, one of the issues, I guess, for some operating systems is that they assume that some remnant of the boot firmware will be left laying around to provide some services.
Yeah.
So that's a question. So in these cases where things have always been done a certain way, which is why we keep doing them that way, you have a bunch of implicit assumptions that result in certain ways of doing things. And when you start violating those base assumptions, it's time to re-examine that system. So
yeah,
if people are, because one of the advantages of Linux boot is it provides an environment where so many more people can contribute to the effort. They don't have to ramp up on some specialized developer environment, set of APIs, etc. And so you've got more people, and with that is going to come the temptation to throw more functionality in there. And when you do that, and perhaps have persistent services, these issues are going to rise. So it would be nice for some group of folks to take a good hard look at that. That's an area of possible contribution. Principal least input validation. there may not be too much to say about some of these things, but for example, the grub parser, which is one example of that. What does Linux boot do about that? And then I think, Ryan, you had mentioned the knit on free as well.
It's such an honor to be able to talk about init on free.
Yeah, definitely Ryan should talk about the grub parser, because from my point of view, the grub parser he's done as part of uroot is a fairly gigantic improvement over the one that's written in C. So Ryan, do you have any things you'd like to say about that? Or
yes, so I can't claim I completely wrote the grub parser. It's an effort by multiple people. But yeah, we essentially have a user mode grub parser, because at the time that we parse the grub, the next kernel hasn't been completely verified yet. So it's useful for that to happen in a safe programming language such as Go, to avoid kind of your typical out of bounds exceptions or invalid pointer or use after free, which can be exploited by an attacker. So Go protects us from a lot of those sorts of attacks in a parser. So that's the big benefit we have in Linux boot, is these things could be implemented in Ring 3, where you're isolated from the rest of the system.
Have you picked up the signed grub configurations?
Inside of uroot? I don't believe we support the standard grub signing.
Some form of signing any configuration that you use between the point at which the controls transfer to Linux boot and Linux boot transfers to the target kernel is going to be important, I think.
Yeah.
Yeah, we just don't want to make it. I don't think we would want to make it be the grub thing. I think because we do a lot of net boot. So I think Ryan, we're doing something right now today, right, at Google. If we can talk about it, I don't know, but
okay.
we would probably look at, outside. There's a lot of signing checks we could do. And in fact, when we were working on this project with Eric Gross near 6 years ago, we were looking at using, almost any of the standard signing techniques, sort of outside grub. So, yeah. Yeah,
I keep pushing on this. It's not unique to me, but I keep pushing this idea that configuration is code. A Boolean that is tested somewhere in your code is just as powerful as an if-def at compile time.
Yeah, absolutely. I ought to mention, just alluding to something Ryan said, grub runs in ring 0. Grub runs with pretty much 0 address protections. If there are problems in that parser, they can spill out all over memory. We have found cases in for instance, UEFI applications where they trashed a piece of memory and Linux got into trouble because of that, some days later, which is a lot of fun to debug, right? So it's hard to overstate the importance of running something like the grub parser in user mode, as opposed to essentially running, as a kernel. And further, Brian, I believe your grub parser has the full range of Go tests integrated into it. So there's a lot of testing of your parser that comes with the uroot continuous integration framework, right?
That's right. There are a number of tests for the grub parser.
It just raised the question, is it worth it somebody taking your grub implementation and a parser and porting it back to grub? But that's not really the topic here. So init on free was actually part of memory safety. Did you want to say something about that?
Well, the issue came up at Google, a little bit of concern that if a Go program processed data that was sensitive data, the one case that we heard that I'm not sure it's completely valid, but might be a little bit valid, is that at least in C, you can kind of never worry about memory you used with sensitive data being garbage collected, and then you essentially lose access to it, and maybe due to some problem, it remains a piece of your memory space containing protected data that is still there when your program exits. And when your program exits, the program's memory gets added to a free memory area, more or less. We'll get around to zeroing this later. And that deferred zeroing was a big deal in Unix in the early 90s when they added it, because it brought you a little bit of performance, of course. But for security, it's a pretty terrible thing, the deferred zeroing. So I think Case Cook pushed this. I'm not sure, but I think that it was driven in part from the Chrome OS world. The addition of options to the kernel to zero memory when it is freed, which is almost ironic. It goes back to the earliest Unix kernels, which did that. But we have enabled that at Google for our Linux boot kernels, and it's probably just a good practice to do that. It costs you, they say, about 7% performance. You don't really care. It's Linux boot. It's supposed to be there and gone in seconds anyway. So I don't think it's a problem to do it.
Moving on to concurrency.
I'll just
go
remind
ahead.
you that I'll just be the timekeeper here. We have a long list of topics to discuss. So
Sorry. Yeah,
yeah.
I'll take it over.
So,
like your call, what you want to do next, but let me know when we.
Okay, let's
do the
try
ownership.
to barrel through some of these then. And I'm going to rely on a conversation that Ryan and I had previously. So concurrency, we talked about check time of use and access to shared resources, and implementation of Linux boot. It's read once, and then everything loaded into memory, and you don't go back to the boot device or the boot flash. And the previous session was talking about silicon root of trust and so on. Can protect that. There's potentially a gap, but more detail we can go into here. Source control, Git externally, Google has its own internally, although it's an open source project, so for this particular effort, it's primarily done in open source. Code reviews, testing, and quality. Ron, you mentioned the grub Golang tests for in uroot. I think that that method is carried on throughout. An example of what should be done.
Yeah, can I mention just one thing? Sure. Every pull request to uroot results in a full Go test, including booting virtual machines, ARM and x86 virtual machines, and doing a full, really comprehensive set of tests of booting and net booting. So the CI on uroot, in my opinion anyway, is really good. And
are you using fuzzing to the extent you think you should?
I doubt it. And also, I will say for a lot of our uroot programs, we need a lot better tests written. Okay, so we're not good on that score, I'd say.
All right. So people could help out there.
We need help. Yeah, we need anyone who can help improve the testing. Most welcome.
I think I'll end on building releases. How do you allow the community, various members of the community coming from various organizations, to have reproducible hermetic builds? How do two people get the same thing out of their builds?
Right now in uroot, we have a test to make sure the build is reproducible. It essentially builds it twice, and it checks to make sure those binaries match. For Linux, I'm not too sure its state of reproducibility. Maybe Ron knows.
I actually have talked to people. I thought that was actually pretty good nowadays, but I could be wrong.
Okay. And anyway, I encourage people to, I'm going to end it here, but maybe we'll pick up some more details in our open discussion. But take a look at the best practice document. And for any project that you might be working on, including Linux boot and uroot and or boot, etc., there's opportunities to improve the quality and make things better. So think that's it for us. Miguel?
Yeah, I'll add that I think it's really the firmware development best practices document is kind of a mandatory reading for every developer doing firmware development. And we've seen a lot of all of the points there have come from true pain points of things we've seen not happening properly,
And
right?
Not just to read it, but to fork it and tailor it towards your own project. Because that document can only talk in general terms, but for your project, there are going to be specific actions you have to take.
Yeah, which is one of the reasons why we went through the effort of actually putting it onto the OCP GitHub. It started as a CSIS, like a PDF document that we thought people would actually want to fork and adapt and modify to their needs. So it's available on OCP Git, and you can and you're welcome and encouraged to take that as a basis and adjust to each specific project. So with that said, let's hand over to Ryan to talk about OSF ownerships.
All right. So I'll give a brief intro to OSF. So actually, OSF, one of the big efforts we're looking into right now is creating the OSF checklist. So this is a checklist of requirements which are needed in order to be OSF certified. So a server vendor would go through this checklist and go through each item one by one, and they'd have to accommodate each item in order to be approved. And our goal is by March 2021 for this checklist to be mandatory for to become OCP accepted, which is fairly soon. So in terms of security, the most relevant item is the OSF ownership requirements. So it's in section 3. So actually put a link to this checklist in the Etherpad if you want to read it yourselves. But this is just an excerpt of section 3, and it describes it's the one that has the most overlap with the security group. So a big aim of OSF is allowing the person who buys a machine or owns a machine to build their own firmware and flash that firmware onto the machine. And a big challenge we see in modern times is a lot of machines have ownership models which are incompatible with that. So for example, one big one is boot guard, which typically prevents you, or in its current implementation, it typically prevents you from flashing your own firmware onto the machine unless you get that firmware signed by the vendor, which is nearly impossible for someone like a hobbyist or someone who has a small company. And we want to change that so people can flash their own firmware onto the machine so that they can apply their own security updates in the future or build the firmware and add their own features. So we had to essentially define what that means, because obviously we don't want an attacker, like we don't want to open up a vulnerability which allows anyone to flash their firmware onto the machine. So it has to be restricted to the owner. So essentially at this point, walking into the territory of the security group. And we essentially had to define our own definition of owners in the OSF checklist, which is fairly vague. The current definition is an owner is someone who has purchased the machine from the OCP marketplace. They would be the owner of the machine, which from my understanding that diverges quite significantly from the security group's definition of an owner. Additionally, the owner must have the ability to perform these 4 tasks. So like I mentioned, they can update the firmware on the machine. But if the firmware is signed, they should be able to sign the firmware with their own key. So sign the firmware image with their own key and flash it on the machine. And this is especially challenging for some ownership models because the key is oftentimes, how do you put it? It's oftentimes fused into the silicon. It's impossible to change after manufacturing. So to enable a circular economy, we require that ownership to be changed at least 8 times. 8 is a fairly arbitrary number, and it has been debated back and forth for hours and hours in our OSF calls. But we settled on 8. It's more than what a lot of firmware implementations allow today. But it will work for newer implementations, like for example, OpenTitan as well as Cerberus, and many other roots of trust. Also BMC signing will allow, I believe, infinite number of ownership transfers. And finally, the ownership transfer must be non-predetermined. So after you own the machine, you should be able to transfer it to anyone. It shouldn't be allowed to fuse at 8 keys at the beginning and the ownership transfer is predetermined. It has to be after the machine has been purchased. So essentially, this is what we've added to the OSF requirement checklist today. I don't know if Ben or Eagle or Ron has any thoughts on this.
So I can say a few things here. First of all, we actually had another discussion earlier today about owner and updater, and the fact that in the current version of the specs they are kind of together, but maybe over time we want to separate owner, which is exactly your definition of owner, the operator of the server, from updater, which is the entity that is allowed to flash firmware and decide which signing keys to use. Another thing that we probably need to discuss here is this tension between the desire of some operators or owners to completely lock the server forever so that it can't be changed firmware anymore, from the OSF and the circular economy need to actually allow systems to pass through series of ownerships. And the way I usually think of that, and it's not like something we've discussed at OCP security, but the way I think of it is that at the end of the day, when you will recycle systems, I would expect that in some cases you will remove the old root of trust and shred it and put a new one and start fresh. But that requires that all of the devices are not locked. Like in your case of bootguard, the processor, if the processor itself is locked, I'm not sure how OSF would allow anyone to change, like Intel microcode on the processor. You could still change maybe BIOS. So I think it would be helpful to define what exactly OSF wants to allow owners to change, right?
So an AMD, it's a one-time fuse. You get 1 key. On Intel, as I understand it, it's three keys, but they'll end up being burned already. And once those are blown, you can't change a single bit of the BIOS. You can't change the BIOS at all. So that kind of model is inconsistent with being able to change the BIOS image, period. It can't be done. So yeah. I think from what I've seen following this for a long time, this model of fusing keys, the way it works, is predicated on the idea that of infinite trust in the manufacturer of the machine. In other words, you assume that you're safe if the only entity able to create BIOS for your machine is the original manufacturer, because that's the model. The model is anything but ownership. So the one thing I'd say when you were talking about owners that want to lock down the key forever, that's not really the issue here. The issue is that the model is the manufacturer locks down the key forever, and the owner never has the option of changing it. So that's kind of a big problem, because So we're trying to get away from that, and what that means is that the last sort of 2 decades of work in tying down these CPUs with these fuses is not really going to be usable for OSF, and we're gonna need to have a complete break with that model of manufacturer ownership of the key.
And so it seems like with
Yeah,
the
but that's the
fuses-
traditional model though, right? So, I mean, there are few different variations to this one. One is OEMs and ODMs fusing the keys inside a platform. That means you're stuck. There is nothing you can do about it from a transfer of ownership perspective. The other thing is OEMs, if you don't fuse the key, if you leave it open, that's a different ownership transfer model. The third one is you leave the key and then you essentially use the platform root of trust as a way to provision and control. Then that's a third, config. So we have to look at all those 3 configs.
Yeah. Now, one thing I should mention though.
First config is a problem, for sure. That's what Ron is talking about.
Oh, say, go ahead. Sorry, what?
Yeah, the first config is a problem because if OEM fuses the key, there is no rekeying that fused key, right? So the limitation in general on a platform is that when you fuse a key, you cannot actually refuse that with a different key. That's where the challenge is. But if you want to overcome that, you don't fuse anything, then you have a different mechanism for controlling the boot flow and securing the boot flow. That could be a platform root of trust chip, as an example. In that flow, you have flexibility.
Yeah.
Yeah. The problem is there were some servers shipped where there was an inadvertent failure to fuse that key, and then there was actual ransomware based on fusing the key and locking you out of your CPU.
Oh, somebody else. Okay, I see.
Yeah. So it's really, I think the scenario of leaving it unfused is just asking for trouble, because not everybody will know what they're getting into, and not everybody is really going to be competent to correctly, get that done. So that's.
I think the thing there though is to not leave it in manufacturing. In the case of Intel CPUs, don't leave them in manufacturing mode, blow that fuse, but don't enable boot guard, and then solve the problem some other way.
Yeah,
it would be nice
that's
to see.
the third option I was referring to. Yeah.
For things like microcode, where it's that configuration, that microcode is actually finishing off the chip's functionality. It's not just silicon. I'm fine with that being manufacturer signed. But for the policy, the operator policy enforcing code or implementing code, such as the BIOS, the Linux boot, UEFI, we need mechanisms outside of the CPU to do that. So perhaps you establish trust between a CPU and a BMC, and the BMC actually feeds the CPU its boot image, which is still signed, or it's just by virtue of the mutual trust, exclusion of man-in-the-middle attacks, but that mutual trust that accepts that firmware image. So there needs to be a little bit out of the box that, just because the only way this is done before is by blowing a fuse in a CPU or the chipset, doesn't mean we have to keep doing it that way.
Yeah, I think we
That's
should
right.
stop with that.
Yeah.
Personally.
I think it's an opportunity here for OCP to say, hey, for OSF compliance, the ownership mechanism for enforcement must not be inside the CPU, or should be somehow.
Focus on, understand what the goals actually are. A lot of times people conflate the implementation and the goals of the policies.
Yeah.
But you've got to leave room for people to innovate. What are we actually trying to achieve? The owner operator wants a certain conforming state in all the non-volatile TCB state of a system, all little devices, fan controllers, CPLDs, boot firmware, NIC firmware, etc. The RAM settings, that whole TCB state is what we want before it is allowed to touch production data. And that is going to be different for repairs flow, and there may be application-specific workloads, like memories configured differently. FPGAs have different firmware, net boot versus local boot. All these things same owner operator may have requirements for different TCB state. How are we going to achieve that? And there'll be dropouts, parts replaced, stuck bits. There might be malicious activity, which is generally very low likelihood. It's generally some transient hardware error. But how do we converge to a system that's actually conforming to the needs for that system, for that workload, for that owner operator at that time? It's not always the mechanisms we've been using historically.
So just to clarify one thing, is the OSF checklist today only applies to the platform firmware? So only the main host on a server platform? So like on a x86 platform, it only apply to the main x86 chipset. It doesn't apply to the BMC. It doesn't apply to the other embedded controllers like voltage regulators and other small pieces of firmware. So just the main host firmware currently.
Yeah, you may be starting to see why Brian said we had hours and hours of discussion on this one slide, and in particular on item C. It is really tough. It's a really tough.
Big challenge right now is no one could change. So we want this to go into effect on March 2021, and no one can change their silicon by then. So we kind of have to live with what silicon currently exists today. Otherwise, we reject pretty much all platforms. So it seems like
there are two sets of requirements that need to be maintained. The ones that people have a chance of being successful to, that are maybe a bit of a stretch but achievable, and what our aspirational goals are, where we want to get to. Give people a heads up that we're not stopping at this set of requirements.
We can map these to the bronze and gold, right? In the security badges, the gold are the aspirational long term. We want to get there.
We talked about that, but it was not well. Ryan and Ben can correct me. My memory is it wasn't well received. I liked it, but it wasn't well received. So.
Okay.
Yeah, so this is essentially why we have an asterisk. So you see on B, there's an asterisk right next to the firmware needs to be signed. Because from my understanding, the security group at some point next year will require the firmware to be signed. So there's going to be a few months between when the OSF spec goes into effect and when the security spec goes into effect. And once both of them are in effect, then this if statement will essentially be moot. Your firmware will always have to be signed.
Yeah, but see, it's two different worlds, right? So the security in general, there has been a lot of this certification aspect that like FIPS compliance, for example, right? There are different compliance requirements, all that stuff. So in general, that's a well bought in. So having a tiered security, badging works. But in OSF context, not many people like that approach, primarily because it's the firmware. They don't see the tiering within the context of firmware. So there will be some challenges in adopting that kind of consistency model because it's two different worlds.
Yeah, I agree in that. So what implementations are possible for OSF? So when the firmware needs to be signed, it seems like with the current implementation of BootGuard, or it seems like you will have to disable it, and you would have to have some sort of BMC or some other chip checking the signature of the firmware.
Yeah, there are multiple options, right?
You'd
in a
want
given
to transfer
platform.
it.
Yeah, I mean, there are multiple options of securing the platform. If you were, like I said, if you were to just follow the traditional model, remember we are talking about the OSF badging now, right? These platforms have been there for the last, several decades, right? So they will evolve over the course of time. But the fact that there are multiple options today, as long as we have an option, or at least one or two options for a given platform that allows us to, change the ownership, and then rekeying the keys is not stopping us to get there, that's okay, right? I know it's not broader from a supportability perspective, that's okay. My point was, if we were to use, let's say platform root of trust and then toss out everything, the provisioning aspect and rekeying aspect that comes with a specific SoC, including a boot guard on Intel silicon, if you can get there, then I think at least it gives us a starting point. As long as it's not a dead end, then we have to work through on what does it take for us to actually add in more flexibility on top of that.
Yeah, that makes sense. So it seems like you would. So what options exist which will conform to these requirements, like allowing at least 8 ownership transfers, and allowing the owner, or as Ben calls it, the owner operator, to update the firmware on their own machine. And
yeah, I think we have good question, Ryan. Yeah,
security group at the same time.
Yeah, I think we have to look at platform root of trust as an option to see if we can actually, avoid all the silicon constructs that prevent us from doing the ownership transfer, and see if we have an option to get there, at least with that route.
Yeah, I was going to say that I think that it's a really tough challenge if you want to apply this to existing hardware that wasn't designed for it. With the PA root of trust, it's kind of like the way to solve this problem in a clean way. Still be secure, still have signature, but then have support for ownership transitions or updater transitions. And as I said, like worst case, when you recycle the system, you throw away the root of trust, not the CPU, and put a new fresh one and continue from there. Right? That's how I would expect most cloud providers who want to recycle their systems to shred the root of trust anyway, and not sell it. So
often there's an implicit implementation in this discussion, or implicit policy, where if a signature check fails, the device will either brick or go into a recovery mode. And an alternative to that is have an attestation based on an identity that's built on the accepted signing key, essentially, or other attributes of the device that can be changed any number of times. So you could have the device always boot, but only if everything lines up will it properly attest to an acceptable boot. And then it's the job of the data center management plane to decide what's going to be done next. Are we going to put it in a repairs flow to bring it into conformance, or is this one of perhaps several options, firmware versions that is acceptable?
Yeah,
Yeah,
it sounds to me like there is an opportunity here to work together on some document like clarifying the owners, updaters, transitions, and how it relates to OSF, and tie it back to the use cases of recycling systems. But I have to say, I think that the solution here is the platform root of trust. It's going to be very hard to solve this without, like, in existing ways where hardware was designed to prevent exactly that.
Yeah. I think one thing I remember from when Chromebook is that I was trying to think of for this case. I think the owner, I almost would say, owner is the entity that can change the key. Because we got hung up a little bit on, how do we define an owner? And my feeling is the owner is the entity that is able to change that key. And then that's kind of how it's defined on Chromebook, and it's slightly that sense. The owner of the Chromebook is the only thing allowed to change the key. And Chromebooks in schools, the student is not the owner of the Chromebook; it's the user of the Chromebook. So that distinction wasn't there originally, but it is there now.
Yeah, but I think we have to
You
make
could
it
also
clear
ask the
that-
question. You could also ask the question: whose policies are being enforced? They're the owner.
Yeah, but I think we have to make it clear to say that, like, the OEM should no longer be the owner once they sell you the machine, right? Because the OEM could just say they still own the firmware even after they sell it to you, which is often the case today. Like, you have to make it clear that the owner is the person who actually, you know, I guess what Ben calls the owner operator.
Well, maybe we should. I mean, we've been using this term for quite a while, but we could use the term policymaker. You know, the entity whose policies are being enforced, and you might be fine with the manufacturer being the policymaker.
Yeah, that's a good point. I think Dell has pointed out that the Department of Defense is actually utterly happy. I believe it was Dell, is utterly happy with the fact that Dell owns the keys. And they're fine with the fact that, you know, the BIOS ownership rests with Dell, not with DoD. This is the way it's been explained to me. I don't think that's going to be true for long, but it's the case today.
And it goes back again to the discussion we started earlier about owner and updater. Like Dell would be the updater here because they own the firmware, but owner is the operator, and they still can set policies, like, for example, which version of the firmware they have qualified and allow, and what rollback policies they want to put in place and stuff like that. There is it's a deep area of I think we probably need to start putting this in writing and clarifying those roles and who is doing what and what is transferable, and in my mind how this all ends up tying to that's the thing that the root of trust enable, the platform root of trust enables. And I think back to your timeline, if you wanted to start enforcing this in March, then I doubt there will be hardware in the market that can already accommodate, but we can start pushing, and then over like I can easily envision how like a year from now this will actually become a reality.
Yeah, that's essentially why we have the asterisk there, like the if the firmware needs to be signed. So currently it's like the easy way to implement this is to just not sign your firmware, which is a bit problematic.
Yeah,
of course.
We don't want to say, please don't sign the open OCP firmware. that would be.
Yeah. So currently, right now, it's like from a security standpoint, it's probably better to have something like BootGuard than to not have it. Yeah.
Okay. Do you want to move on to the next discussion? Do we feel that we've covered this one?
Yeah, maybe Ron. Ron had an experience with this before, where I don't know if Ron, you want to like share your anecdote on how you got a server and you were unable to update the firmware.
Oh, well, no, it's just an experiment we did. We had a Dell server at Google in Boston or Cambridge, I should say, and we just did the experiment of changing one bit. And when we changed one bit and rewrote the firmware back, it came up, and then it paused for a while, and then it came up again with that bit unchanged. So evidently the BMC will detect that and quote unquote repair it. So, you know, obviously this is not a great situation for a company like Google. And, you know, that's just the kind of thing you run into. Is that what you're thinking of, Brian?
Yeah, I think that also the other part is oftentimes the OEM, they're not fully like well versed in the terminology of owner, or how the ownership model works. Like sometimes we speak with them and they're not familiar with BootGuard, or they think that boot guard is disabled when it actually is enabled, or vice versa.
Mm-hmm.
So I think that there's a big opportunity for, like, in the industry to, I guess, how do you say it? Like, teach people, or I don't know, like outreach to explain these concepts.
Yeah. It's pretty darn complicated, and a lot of the manufacturers don't really want to be BIOS experts. So you end up with a situation where you have a fiendishly complex firmware model in the hands of people who really, they're just trying to ship a product, and they don't really want to deal with this complexity. So the result is, yeah, mistakes do get made, as in the shipping an unfused chipset and leaving yourself open to a really terrible situation where your hardware suddenly ends up completely bricked.
One suggestion too, we need to keep separate the roles, owner, firmware update, or whatever, and then the mechanism that we use to transfer the ownership, because they're separable.
Yeah.
Okay,
So
let's move.
I had a sorry, I just had one question, right? So there is platform firmware that can be signed by OEMs, and yeah, I guess you can implement ownership transfer, right? But what about things like microcode, for example, right? That has to be signed by the silicon vendor, right? Or I don't know anybody who does it another way. So how does this apply, or does it not apply to microcode?
I mean, I think it's generally accepted in OSF that microcode is below the level at which we swim, but also I may have misunderstood your question, but microcode's been kind of released under BSD licenses for probably since 2002, redistributable. Was that your question, or did I not quite catch it?
I think that was my question. So what you're saying is a silicon vendor can have some components that is completely owned by them, right? Even though it comes out of the SPI flash, for example. And
Yeah,
that need not be subject
Yep.
to device ownership transfer.
Oh,
That would be my take. Yeah, there
Yeah.
are certain pieces of there are certain class of devices and types of firmware that manufacturers would say, I'm not going to open that up, and microcode is probably one of them. And I think we have to accommodate that.
And keep in mind,
not to confuse on this ownership thing, right? So there will be certain components in a platform that are actually owned and controlled by the vendor, right? So the microcode is one example. What we are looking for is that there is a way for the microcode to be readily available when you do the transfer of ownership. That's one element. The second element is that how do we bring in the security element for those binary, aspects in a platform, microcode and, ROMs, and make sure they are secure. And there is a way to actually, modulate the security aspect on top of that.
yeah. I do want to make, I do understand what you're saying. I heard that word opening in. Remember, OSF isn't about open source. I mean, we would like it to be open source completely, but we explicitly accept blobs. So I just want to make sure that we weren't bringing that in again. We're not saying that everything has to be open source, and therefore it's not exceptional that the microcode is not open source, because open system firmware doesn't require open source.
Ron, can you clarify when it does and when it doesn't, please?
Technically, it never does. I mean, it only requires that a customer an owner be able to take the firmware and change it and then reinstall it. And that could be as little as taking a logo and changing the logo. And if you know, obviously most of us would want to be able to take it and change it by adding open source components to it, but we actually don't require that.
I think that's exactly the great segue to the next topic, which is what firmware should be allowed and can binary releases ever be secure? And we kind of started touching that, so
Yeah.
let's dive into that a bit more.
You're welcome.
So Ron, do you want to take that one?
I'm sorry, who?
Ron.
Oh, you know, I feel very strongly that binary releases are just a time bomb. And I've been trying to make this case for over 20 years now with partial success. So in my ideal world, nowadays, the firmware would be very small and would be 100% open source. And I ought to mention here that in the year 2000, we had GPL firmware 100% open source that ran on Intel, AMD, PowerPC, and Alpha machines. Same code base. So I know it's possible. It's just a matter of whether the various CPU vendors allow you to do it. It's never been a matter of whether it's possible. So I don't like binary owned releases for firmware any more than I like it for kernels. And I wish we were back to the world we were in 20 years ago when it didn't have to be that way.
So should OSF try to push it? You said OSF is not about open source. It's we accept binary packages, but we don't like it from a security perspective. What can OSF do to push?
I think we should push it really hard. We've been my hope has always been, and I'm actually gradually starting to see this happen, that we would find some market force that would come to bear on the vendors. And I think at least in part that market force is security. But you know, Chromebooks have done a lot of good in here because Chromebooks have really done a lot to claw open the laptop world to accept a lot of open source in firmware where there was zero before. And if you get an ARM Chromebook, you're going to get it mostly open source. If you get x86, it varies. But the one thing I learned when I was doing this in the DOE labs, which was a problem, was that a lot of vendors would promise to deliver the open source and ask you to make it optional for flexibility and then never do it. And then, of course, I started Linux BIOS. I didn't realize it at the time. I started Linux BIOS right at the time when the microprocessor world was changing, and they just simply didn't want you to be able to write BIOS anymore. So not 4 or 5 years after we were successfully shipping code, the chipset owners decided they didn't want us to do that. So I think OSF should push really hard. I wish they had pushed really hard in 2010 when the OCP started to put. I tried to argue with them to do this, but I didn't win the argument back then. But I'm really thinking OSF now can push hard on open sourcing the firmware. It's really critical, and it's really critical that it be open.
Yeah, it takes effort though to make a source code release and support it. And if people are going to do anything with it and have questions, to have people to answer that. So I think some of that was just being pragmatic. But to deal with, especially the requirements of large-scale data centers, and to deal with the complexity of systems, I think the tide turned some time ago where it is effectively cheaper to have an open source project for firmware than it is to have a closed sourced one. There's kind of a related topic. What's your opinion of encrypted binaries? So I see a couple of use cases here. One, people I respect say that encrypted binaries are always more secure. And I can actually see a valid use case if a chip does not have secure on-package storage, that to have a per-device key that encrypts data in an off-chip storage. I can see that as valid, but I don't really like encrypted boot firmware, for instance, because it makes it hard to audit it. It makes it hard to tell if the system is actually conforming to my requirements. So that's a couple things there. Is it now cheaper to have open source firmware? And then what's your opinion on encrypted binaries? Ron?
So I was kind of there for the big Unix to Linux transition, and I watched the old guard just fight so hard against Linux because their view was that Linux was an IP leak. And then I kind of watched them all realize that while they had all been independently maintaining their own copy of Unix with all its weird warts, all of a sudden their bug fix team and their code team was the world. And so it was, you could kind of see the light go on in the heads of all these companies realizing that their QA group had just grown by at least a factor of 10, and their competitors were now helping them fix their kernel. And at that point, it was inevitable that Linux was going to kind of rule the day. And there's a lot of argument about this. I think the GPL was actually a big key part of that, but we can argue that until the cows come home. But I think that the same effect actually started to happen in the early 2000s. I saw it happen with various vendors where we had a common code base for firmware for HPC clusters, and people could share knowledge and improve their systems. And they realized there was more advantage to sharing than to not sharing. It saved them money and time around bugs. So I think we're right back where we were 20 years ago, except maybe this time people will really realize that it really is better to be open and to share fixes and to share code. So I'm hoping that this time around it works out. Encrypted binaries. Man, I don't know what to say there.
Yeah.
I'll say something. I think encryption is like it's not security for code, meaning we've seen enough cases of how people can reverse engineer anything. One of my favorite all times talk about that is from Black Hat. Look for something called God mod exposed in some VR processor, like masterpiece in reverse engineering. I think encryption is valid for IP protection. Like some vendors want to make it harder to reverse engineer their code, but it's not a security measure in the sense that we're talking here about that, like to actually prevent vulnerabilities from being exploited or hackers to find those vulnerabilities. It adds a little bit of a hurdle, but it's not a true security in this sense, in my opinion.
I think there's a special case for binary-only releases where they actually contain open source firmware, and that's acceptable because it's under like a BSD license. So people look at the binary and they notice the assembled code contains the same pattern as if someone built something like EDK2. And it's problematic in some cases because there might be security patches to EDK2, but you're no longer able to update the binary-only release yourself. You're kind of relying on whoever built it originally to update it because it also contains code which is proprietary. And I think in that case, it's less secure.
Dawal Kamar has a comment. With respect to encryption, imagine a scenario where a fix for a vulnerability is released before it can be deployed by everyone. Adversaries create an exploit and take over unpatched systems. Basically, your patch release, your fix, compared to the previous release, points the finger right at what your zero-day exploit is.
But that's true with and without encryption. Again, encryption would make it a little bit harder, but they will figure it out. So if you rely on encryption as your security mechanism, you are doing the wrong thing.
I think I kind of agree with that. I would say that there might be a benefit to encryption, but it's been abused far more. It's been abused, in fact, so much that I think if we consider the balance, I'd say I don't really like it, just because I'll assume that 99 times out of 100, it's not a legitimate need.
So people are using it as a crutch. They say, there, I fixed it once and for all.
Yeah, I encrypted it. It's fine. It's not.
Yeah.
Yeah. Like everything can be reverse engineered. I think we've seen enough examples of that to understand that if the purpose of the attacker here is to understand your code and find when the vulnerabilities are and exploit them, and you think that you encrypt the package and therefore you'll make it impossible for them. No, I think you've just made it more challenging and fun for them. That's what happens.
So this, I think that brings up, we've got a note here, a case study, the AST 2500, basically a case of security through obscurity. No one could ever possibly find this very long, garbage-looking password that we have embedded in our system. You know, just like any other flaw, no one will ever find it because it's too hard to reverse engineer it, or it's too hard to decrypt the binary. It never should have been there in the first place.
Yeah. So I ought to mention that Aaron Koshi at his company did analyze 100,000 UEFI firmware images and did find many, many, many instances of LoJack. He found SendMail clients. He found SendMail passwords. He found things that would do uploading of all kinds of stuff, things that phoned home. I mean, we have enough bad stuff embedded in that isn't encrypted that I just don't see it as being a good idea.
Right, and the question is, how do we eradicate that? And more transparency, I think, is the best answer anyone has so far.
Yeah, and that means, to me, open source.
Yeah.
So back to the question, back to the open source nature. So what in the OSF checklist encourages vendors to open source?
Open system firmware, right?
What in the open system firmware checklist encourages open sourcing?
Yeah.
Is there something there?
Well, there is, because it's kind of subtle, but it's there. And if we consider UEFI, we built a tool called UDK. Thank you, Ryan. Thank you, Ganshun. That allows us to rewrite UEFI firmware volumes, and in particular, remove things and to add our own things. And so, sure, open system firmware doesn't explicitly require open source, but by its nature and by the nature of UEFI, it enables a gigantic reduction in an amount of binary components in UEFI and a replacement of those things with open source things. And in our case, a Linux kernel and a Go userland. So when we enable people to reconstruct a BIOS image, we enable people to add open source components and get rid of junk. And we see that happening every day. In fact, I was just reviewing a list of the number of companies using Linux boot, and in particular using Linux and uroot, and we seem to add another company every month for the last 3 years now. So I feel that while we're enabling, we're not requiring, but the enabling is really very powerful.
Is there some
so can I
encouragement and like rewarding openness?
I think the reward is you remove every single bogus network protocol stack from UEFI, along with the HTTP downloaders, uploaders, servers, and REST servers, along with the USB stack, which causes machines to boot and fail to enumerate USB sometimes. You know, it really, I think the encouragement is we can remove things that put your system at risk. And that's a lot of encouragement. And we should document that more. That would be my one thing. We really need to talk more about how we can get you a safer machine by basically cutting things out of the firmware image.
Of course, counter arguments that people try to make to that is, well, then you're throwing Linux in, which is enormous.
Yeah, but and then my counter argument, I'll counter argue, is that I've really been watching a lot of what, again, Case Cook and a lot of really smart people have been doing in Linux in the last couple of years for hardening, and it is impressive. And I never expected them to go as far as they have with the things they've done. I'm not claiming that Linux is a secure kernel, right? I'd never make that claim, but having looked at a lot of the UEFI code that companies release and then looking at Linux, no comparison in code quality. Linux is hands just leagues ahead of where the UEFI code base is. So I would say that I'm okay with that trade.
It's also worth mentioning for OSF, we're approaching this one battle at a time. So the big battle for the first version is redistributable firmware. And then hopefully that will let us move to open source firmware in a future version of the spec. But right now, you can't even redistribute lots of firmware images, which is like even worse.
Yeah. Someone was going to say something before. Yeah.
Yeah. So I had a question, right? So can you delineate for me how you would differentiate what would fall under something like firmware versus microcode, right? What should be open, what shouldn't be open, right? Because we're saying binary only is also allowed, and we're saying, yeah, we want to move towards in a more open world. Right?
Well, Elaine is here, and so lest we forget, the PowerPC microcode is open source, as I understand it.
Yep. Instruction set, everything.
So, we have a QED that is doable. It's just that, it's a choice that vendors make not to do it. There's no technical barrier.
Look at the
look at
context of
OpenTitan.
why do we need
look at
to
OpenTitan as the
open?
extreme openness, right?
Yeah.
These are, I mean, there are products that are not finished or are only, 90% in silicon, and really you need to load up some gates and fuses and microcode to finish it off. It's really something that only the folks with the fine detailed knowledge of the silicon can actually write. Whereas something, the maturity of IBM products going way back, they, implementing new, edit and mark instruction in PowerPC, it's fine. That's a little program. You could add your own. They're just different levels of maturity and target audience.
Yeah, I mean, the other thing I would add is, you don't open source just for the sake of open sourcing, right? It's not like, if you look at it from the vendor perspective, what is that? Why would you want to open source? So you have to see the benefit for the ecosystem. So for example, open sourcing a microcode has no meaning to me, in my opinion. But open sourcing the platform code, absolutely, because it is something that virtually every part of the ecosystem will benefit and contribute to, and that has a tremendous value, right? Open sourcing the BIOS portion of the story will also have a tremendous value. So it really depends on, and there is a complexity element too, right? So let's say if you take the UEFI firmware, has thousands of lines of code. Let's say you open source it, right? Who understands that? Specifically, if there is a vendor portion of the open source component that requires reading through hundreds of pages of document, there is nothing, the community will come and contribute and help. So it's good from the open source perspective, you can check box, but the value that the ecosystem will benefit is virtually nothing for certain pieces. So we have to be careful when we say, open source is good for everything.
I think maybe you make a good point, and I would distinguish between open source as in I encourage everyone to contribute back, and opening up or transparency as in this is what we do, and it's all out there in the open, which you get trust in return. Maybe you don't get community contribution, but you make your code much more trustworthy when you do that.
And
So
I like
think
that
that's a
distinction.
strong reason for me to open up. Ben, you were saying something?
No, I think
Yeah, good.
I agree with that.
Yeah. Okay, so let's move on to the next discussion. I think Ryan, you wanted to lead this one already. I don't remember.
It's a good topic. I would rather hear from rest of the team. Maybe Ryan, did you put this one? I don't recall this.
That'd be me.
Ron would have the
okay.
next.
Go ahead, Ron. Yeah, would love to hear from you.
So yeah, this kind of got put in, and all right, I'll try and make this quick. So I think when I try to explain SMI, what I try to explain is the promise you get on a PC, x86 PC, is that it'll run everything written in the last 40 odd years. It'll run DOS 1.0. And I have a longer story, but the short form is there are some monks in a monastery in Nepal. This is a true story that depended on the fact that they could write a DOS program that would rewrite the fonts in Hercules graphics adapter that still can be, functionally used in a PC to display the polytext, which is a religious text that they actually typed in and put on a floppy disk. So there's your promise, DOS 1.0. Well, the problem is it's 1991 and you have a laptop and you close the lid and you want it to sleep and you can't go back in time and teach DOS 1.0 how to do that. And so what was done, and I think Intel led this, and it's actually pretty amazing when you look at how it all happened. They added an entirely new protection mode to the processor that runs at a higher privilege level than Ring 0. And all the write-only registers that came with the original Intel chipset on the IBM PC have a read-only thing sort of behind them on the other side of the wall from you. And system management mode, which is entered from a system management interrupt handler, can see all those read-only, write-only registers. They can see what's in them. So system management mode, new processor privilege level, it can see all the things that you can't see. So when your kernel, like Linux, writes into a write-only register, it can't read it back, but SMM can. So it's actually a higher privilege level than Linux. It can see all of RAM. And beyond that, Linux is not able, or any kernel, Windows, is not able to see the memory that contains the system management mode code. That was originally a 64K segment. It's now an 8 megabyte segment or even larger on newer CPUs. It was originally pretty simple. Now it's fairly complex. And one of the problems is, yes, it can see all of memory and it can also execute code from anywhere in memory. If it doesn't properly validate input, it can trash memory. And it's really actually been shown to be a pretty good place to hide a rootkit, because once there's a rootkit in SMM, there's no way for the kernel to know that's happened because it can't even see the memory. And in fact, the chipsets are so powerful that if you have, let's just say, 64 meg of memory and SMM needs 8 meg, when Linux comes up, the hardware will only show it 56 meg of memory. It'll only show it that there is only 56 meg of memory. It's as though that memory has just essentially vanished. So if you're really looking to do an exploit, SMM is really as good as it gets. It's where you want to be. SMM handlers do all kinds of stuff. And one of the discussions I've had with x86 vendors is, when are you going to stop using SMM? And what they tell me is every time they pull something out of SMM and put it somewhere else that a kernel can access it, the hardware guys design some new hardware thing that requires SMM to be there. So as quickly as you empty that bucket, it's being filled by hardware people. And for example, on some newer AMD processors, if you want to write flash, you've got to go to SMM to communicate with the thing that'll let you write flash. And I believe the Intel 3D X point requires an SMM handler for initialization. So these are new pieces of hardware, right? These aren't 30-year-old pieces of hardware, even though SMM is 30 years old. So every time some new fancy piece of hardware comes out, it seems like an SMM handler comes with it. So do they exist? Yes. Are they still needed? Yes. Will there be a new use of them tomorrow? Almost certainly. What can we remove? Well, one of the biggest uses of SMM is for RAS. And when I was at Los Alamos and the Optron first came out, I'm pretty sure it was Los Alamos. I looked it up again. We kind of tried to pioneer doing the RAS in Linux, and that effort was called Blue Smoke. And it's kind of still around, but since that time, really the vendors have doubled down on putting RAS into SMM because, to put it bluntly, to do RAS properly, you need to know some secrets. And those secrets, it's desired not to leak those secrets to the kernel. So again, this is the conflict we see all the time, sort of between binary components in BIOS and leaking information about chips. I could tell you a long story. We don't have time about Lawrence Livermore National Lab, the Itanium, and the attempt to try and find out where the parity errors or ECC errors were occurring. So grab me later and I can tell the story. So what can be removed? Well, you can remove some of them. We can remove the USB stack from SMM. Yes, indeed, there was a full USB stack in SMM. That's why your USB mouse worked back in the day when you had a kernel that didn't have USB support. I think it may still be there in a lot of cases. You could remove it, though, I think. No reason to keep it. And the one danger with SMM I should mention, every once in a while, companies will write SMM handlers, and those handlers call out from the reserved SMM memory outside to memory that is not SMM controlled. And if you are smart and figure out where that SMM handler is calling out to real memory, you can change that and corrupt SMM, and that's your path to a rootkit. That's called an SMM callout bug. Is there a next slide, Brian? I don't remember.
No, I think that's the only slide
Okay,
we have in
that's it.
SMI.
So that is SMM. That is why SMM frightens me. I did a talk at the Core Boot conference about 3 or 4 years ago, showing that I could, in fact, redirect every SMM interrupt to the Linux kernel and have handlers in the Linux kernel for SM interrupts. One big win on that is, by design, SM interrupts, when they occur, halt every core in your machine. If you have a 500 core machine and there's an SM interrupt for anything, like, I don't know, I've actually seen this in practice on some things. A USB keyboard is attached and they forgot to turn off the SM polling that was there to support the USB keyboard. I think that was the situation. Every umpty-ump milliseconds, every one of your 512 cores is going to pause for an SM interrupt you don't need. So I would like SMM to die. I've been wanting SMM to die since 20 years ago when we originally did Linux BIOS and then Core Boot. We actually disabled SMM because we were in the HPC community and we knew what a problem it was. It's kind of come back into Core Boot due to customer demand. I still want it to die.
It's probably worth doing the math on that. You say it costs every one of your cores so much at Google scale. How much heat is that? How much power is that? How much money is that?
Yeah, I don't even want to think about it. I know it's a lot. Or even, you look at Amazon scale, yeah, it's a lot. So, yeah, I would like SMM to go away. The problem is it's just so darn convenient, because if you have a hardware widget and, you really don't want to release the details of that hardware widget, it's just buried in the SMM. And by the way, I don't know how many people know, but SMM, there's actually a hardware filter in your I/O chips that looks at every single in and out you do, and SMM can trap all your ins and outs, your I/O operations, and filter them. And so the question is, when I talk to my hardware, is it in the loop or not? Well, SMM is also able to run in a way that the clocks pause, and you actually don't know how much time passed while you're in the SMM. That's by design, because guess what? DOS 1.0 wouldn't know what to do if the clock was jittering all over the place. I've written code that can show you how much that SMM is costing. It's called the fixed time quantum benchmark. we've used it to show, you know, the effect on HPC applications over the years of having SMM in there at all. That's why we want to disable it on any HPC system. So I think that we would like to get rid of SMM. I've become a little pessimistic that it will ever be possible, but I think that we should definitely talk about making the effort, because from the point of view of security, it is a really serious problem. One last thing I'll mention, you hit a power button on your PC, that involves ACPI and that involves SMM. So SMM and ACPI are entwined, intimately entwined. It's very, very hard to figure out quite at the moment how we would rip SMM out when we're using ACPI. I mean, I can't say I really know, but that's kind of the nature of the scope of the problem. It really affects everything. You consider that you can't really run your power button without SMM in the middle somewhere. You know, that's kind of a problem.
So maybe
and-
get maybe
and
a
which-
benchmark.
Which
part of the
SMM
sentence
handler? Which SMM handler would you eliminate first? Is there
I don't
one
know.
or a class of ones that you target first?
I'd probably take the USB stack out if it's still there. That's the problem. You see, I don't know what's in there. I can't look at any given platform except a Chromebook and know exactly what's in there. And there are problems because the power off handling in all your systems probably goes through SMM. Certainly if it goes through ACPI, it does. So, and again, the ACPI is there to kind of hide, you know, details of the power management, you know, on your system, right? It's sort of a generic handler of events that turns into a specific handler for your system. So we've kind of gotten into a big binary blob dependence in the last 20 years on ACPI and SMM, and unwinding that is not really easy, but we could certainly start.
Yeah.
So UFI
on the-
updates need to go through SMM, right? UFI capsule updates.
No,
No?
you don't. No,
Okay.
I mean, unless you, there will be certain elements that you may have to do, like, you know, you want to do the firmware update without shutting down the platform. You know, some of those constructs you have to go through. But, you know, let me just step back a little bit. So I think in general, within the context of OCP, what actually causes the use of SMM and why, right? There are several artifacts that require. Some are really because of what Ron was talking about. You know, it's just used as a mechanism to say, I'm going to do something behind the scenes that is more privileged than ring zero, like DDRT, you know, like scrubbing, for example, right? There is that element that is actually, you know, coming from the x86 vendors. Now, within the context of OCP, there is a working group that is actually going on, RAS working group, essentially looking at all the requirements that are needed for RAS. I think we have to look at those, you know, RAS elements and say, can we actually implement that using the OS first model? In general, the direction is we need to be looking at OS first initiative as opposed to firmware first. The moment you say firmware first and runtime RAS, you're back into SMI handler. So that is one focused activity that is happening. The other thing is we have to look at and see if we were to open source the SMI handler, will that actually get us to have, you know, having a more secure implementation? Just the open sourcing element, you know, does it really help? One is reducing the dependency, right? The two is open sourcing aspect. Will that help from, you know, getting to a secure, better security as opposed to where we are today, which is really, you know, opaque, binary. You don't know what's happening.
Yeah, if there is secret sauce, it goes back to the point about, yeah, even if you open source, it's not necessary that everybody is going to, you know, look at it and understand and go through this 1,000-page spec, right? And to add to that, ARM is actually doing a pretty good, or I think is doing a pretty good job of it, right? By moving, you know, using trusted firmware and things like that, and moving RAS and essentially standalone into a open source model and deprivileging it.
Yeah, no, I think ARM is really.
That's a direction I would like to see even for the x86 ecosystem, right? The standalone open source. So there is no, hidden aspect, right? The problem starts once you have a hidden aspect. The moment you take that portion out, at least it will start with open sourcing, and you have a clarity on what needs to be done, and the rest of the ecosystem can play in it and then make it secure. Totally agree.
But does it really improve security if nobody's looking at the code, right?
You're right.
We have the same problem with the Linux too, right? If nobody's looking at the code in Linux, why will that be secure? I mean, the Linux is not, Linux kernel is not a small, few lines of code. It's thousands of lines of code. The assumption is that there is enough firmware ecosystem out there, open source ecosystem and developer ecosystem. When you open source it, they are actually able to be part of that and play a secure role.
Yeah. I will. Yeah.
Yeah, like I would expect the hyperscalers who are going to adopt it to actually review this if it was completely open sourced.
Yeah, I mean, they have to, right? Otherwise, how can you trust deploying certain piece of component sitting on your, fleet of servers that are thousands and expect that it is secure, right? I mean, they will be super paranoid about that.
I was driving those security reviews for Microsoft Azure, and I can tell you, if it was open source, we would put people to review it. Absolutely.
Yeah, if you want to learn more about SMM, you can look at my talk. Get a hold of me if you can't find it, but it's one of the open source firmware conferences that I explained it a little bit after having had to relearn how to write it. And the core boot SMM code I think is pretty good. So it's out there and it's worked for well over a decade. It's shipping in a Chromebook, tens of millions of Chromebooks. It's pretty hardened, and that would give you a good view of just how crazy. SMM is really crazy because in SMM mode, certain memory locations are now registers. It predates model-specific registers, so some aspects of it are just head-scratchingly strange. But the core boot code is really good about handling it.
So one quick question, right? So with regard to things like boot ROM or even firmware, right? What if you find a flaw that is unfixable, right? That has financial implications to these silicon vendors, right? So, yeah, I'm trying to understand what is the incentive for them to actually, open source things like their boot ROM or even these RAS handlers which might expose secret sources or secret hardware.
I mean, one answer to that, the Linux BIOS code. We in Linux BIOS had to write the code to enumerate the hypertransport topology for every possible topology, like the weird eight-way hypertransport. And we wrote the code that would dynamically determine the hypertransport topology. And we later heard from AMD that our code was better than their code, but they couldn't release their code and they couldn't use our code because it was open source. So, vendors might just discover that the community would give them better code than they can write themselves. This has happened more than once, certainly in core boot. So I think the idea that, you don't want to release this kind of thing because people will know what you got. Yeah, I can understand that impulse, but at the same time, you are making it possible for people to give you back something better than you could do yourself.
Yeah, the concern is if you find that after you've sold 1 million chips, right, and you find a security flaw, and now that's.
But the other thing you've got to keep in mind, and I dealt with this back when I was at Sandia National Labs working with DHS and other organizations, the amount of money that organized crime and nation states devote to finding these vulnerabilities would really make your head spin. So it's not like the only people discovering vulnerabilities are the people who make the chips. There are unbelievable levels of resources devoted day in and day out to finding vulnerabilities. And I think these companies have a lot better shot at surviving this kind of event if these things are open than if they're trying to hide it and the only people who know about the problems are the bad guys. So I think we're way past the point where the model is, I shipped 1 million things, I discovered a vulnerability, I don't want anyone to know about it, right? But by the time you've shipped however many things it is, somebody, you know, and I heard the joke actually, you know, the people who used to ship drugs out of their barns in various parts of the world now have machines, and they do decap in these barns, you know, out in the middle of nowhere, so they can try and find vulnerabilities. I mean, this is passed to me by a professor at ETH Zurich, and he was dead serious about it. So, you know, I think we have to accept that the people attacking your system are well-funded and really motivated, and you're better off being open.
Yeah.
How are we doing on time?
We're out of time.
I think we're done. I think
know.
we're
Okay.
okay. So let us wrap up. I think this has been like a great discussion. We also wanted to do a discussion around how to incentivize vendors, but I think we kind of touched it throughout the discussions. So it could be a good follow-up discussion sometime, but we're out of time now. So I do want to point people at resources back to open to secure firmware and our main topic of the day. You have links here for relevant
So
documentation.
paste those links in the shared doc on the conference page there. The Etherpad.
Yes. Yeah, I can't do that because I am not connected to the FM virtual, but maybe later we can share it. And the deck will be available. So those are all links and people can download the deck. And with that, the call to action here is please review the OSF checklist and the secure best practices and join us and help shape the future of more secure hardware. And I'd like to thank everyone who participated in this lively discussion. It was a fun discussion. I hope it's the first of several. So thank you all for attending and participating.
Thank you very much. I really enjoyed it.
Thanks a lot, Igor.
Thank you.